Okay, so welcome to the talk about Jaeger, Introduction to Jaeger. So as an agenda, we will give a brief introduction to people what tracing is and why we use it in case you don't know that. So we will, how many people do you really want to see live demo versus screenshots? All right, I mean, I'll try to sort of improvise on the fly. There's a Docker compose file, so it's not that hard to run. But I'll still probably go to the screenshots because it's kind of annotated, easier to just explain. And we'll talk about project status overall as a CNCF project. Jaeger has graduated project since October. And we'll talk about roadmap. So do you want to introduce yourself?
So hi, I'm Pavol Loffay. I'm a software engineer at Red Hat. I'm working on Jaeger, open tracing, and open telemetry, and a little bit on tracing in service mesh in Kiali project.
I'm Yuri Shkuro. I'm from Uber. I also maintainer of Jaeger and open tracing, open telemetry. And as you can see, I also published a book earlier this year on tracing. It's first in the industry tracing book. So point of pride for me. But other than that, yeah, you can check it out. What's that? Oh, is it?
Sorry. Here, I'll take that. Try that one.
How's that? Better? Yep. Yeah. Cool. All right. So yeah, if you want to interested in the book, check it out. It has a lot of basically basics about what tracing is, how to use it, how to deploy it, which is actually the hard part usually with the tracing. So let's start quickly with what tracing is and why. Basically, the need for tracing appeared in the industry when systems became like very complex. So we started building distributed systems which were not only kind of scaled wide by replicating the same service many times, but they also started scaling deep where you have multiple layers of services or microservices in the architecture. And it becomes really, really challenging to actually figure out what's going on in those architectures. So here we can see a screenshot from Uber. This is like done by Jaeger, the data collected and visualized by Jaeger. So it's a service graph. Nodes represent services. Lines represents connections, like RPC calls between services. And a transaction which comes from mobile app to the backend might look like this. It can touch like several dozens microservices, hundreds of nodes, potentially include hundreds of RPC calls, right? And so if you are on call for a particular service and you have an SLA of, let's say, your latency or your error rate is supposed to be within certain limits, and suddenly, boom, you get an alert, your SLA is broken, what do? Well, okay, great, you have a service, but your service in a deep microservices architecture probably depends on a whole bunch of other services, right? And so any of them can be responsible for ultimately for the error, but you're the one on the hook because your service is still broken its SLA, right? So you need to do something to fix it, even though you may not have a control to actually fix it. So the only thing you can do is at least isolate the problem and say, okay, well, I need to page that guy to wake up and like fix whatever. Or maybe you can route around the problem somehow. And so distributed tracing helps you with that, basically. It, unlike other monitoring tools, distributed tracing allows you to figure out what's going on in this complex architecture, right? And you might ask why, like, what about other monitoring tools like metrics and logs? And so the difference between tracing and the monitoring tools specifically is that monitoring are the things that you know up front you want to measure, like your SLA, for example. You say, I want to measure all the error requests and say that I should not have more than 1% of requests failing, right? So that's the thing you know up front. You measure it, you set up an alert on it. Great, metrics are perfect for that. But once that alert fires, then what? can you continue using metrics to actually troubleshoot that problem? And the answer is usually no, because, well, you might, but it's very hard. Because metrics are focused on an individual node. So if in that picture, if you're at the top of the pyramid and then all these downstream services are below you, you kind of have to go through every service and look at its metrics. You probably don't own that service. You probably don't even know where the dashboards are for that service. But if you know, you may not understand those dashboards because, again, you don't own it. So doing that by metrics is kind of very hard. And plus, it's actually n square problem because the pyramid, right? The height is, the surface of that pyramid is proportional to the square of the depth. And so the deeper the architecture, the more stuff you have to look through to understand where the problem is. And similar thing with logs. Logs is what you typically use to troubleshoot problems, right? You don't use logs for monitoring. Well, you might again, but like usually you go to look at them when something goes wrong. But you have the similar problem. You have this like n square number of potential points where you have to go and look for the error, for the explanation. And so, but traces provides the correlation across all those services, and it actually allows you to narrow down the problem much faster. Traces, you can think of them as like as a stack trace for a distributed system. And so how tracing works. The idea is actually very simple. You probably may already be doing that in your applications anyway. So when the request comes to like a front-end service, we assign it a unique ID, and we make sure that that ID is propagated through all the execution of the request through the call graph, right? Deceptively simple. Somewhat hard to implement in some cases. But as we do that, what that allows us to do is if we also, in addition to propagating the ID, we collect some telemetry and sort of send it out of the process to the central backend, like Jaeger, then you can reconstruct the execution of the trace later on into a graph or a Gantt chart or time sequence diagram. And basically, you can reason about which services were executing the request, were there any errors in them, and so on and so on. So yeah, that's sort of, again, the idea of tracing is kind of very simple. It's not new. It's been around for like 15, 20 years maybe. There's lots of academic papers written about it 15 years ago. But it's just getting now into the mainstream because more and more organizations are switching to microservices. And microservices are very deep systems where you experience these problems that we didn't have before. So so many people raise hands for live demo. I'll try to do that now. Close some secret Uber stuff first. So I already had it running, but I will restart it. Oops. Is Docker Compose smart enough now to fix the typos? So this is you can go to Jaeger repository example/hotrod. It has basically this Docker Compose file, so you can run it very easily yourself. It's also this URL bit.do Jaeger-hotrod is a blog post with a walkthrough that sort of demo in a lot more details if you want to try it out. So while this is starting, you can see here there's two services that I'm starting. One is the actual Jaeger backend. We have a component in Jaeger called all-in-one, which kind of in a single container encompasses all of the Jaeger components all at once, right? So UI, like collector, storage, in-memory storage. So it's very easy to run. And then hotrod is the actual demo application, which is instrumented for tracing that I'll be demoing. And so it has a URL here somewhere, this one, so I can open that. So here's that application. I'll make it bigger. It's sort of a mock ride-sharing application where you have several customers, you press a button, and the car comes to that address, right? So I can do this, let's say, request, and we can see, okay, well, there's a T number something C, that's a New York style license number for commercial drivers. So that's what usually looks like at Uber. So it's arriving in 2 minutes. You get an ETA, you get some additional like information, specifically like latency and some request ID, which we might get into in a moment. And so again, we don't know what the application is behind the scenes, so let's look at that. So here's the homepage for Jaeger. And first thing I want to go to is the dependency diagram and switch to this view. So I executed a single request against the application, right? Jaeger automatically built a service graph by observing what happened within the application, how the services are connected. It has this picture. Basically tells us that there are 4 microservices and 2 storage components in that one single microservices application, right? Of course, they're all simulated in the like single binary in practice, but actually that binary talks to itself through different RPC calls and different protocols. So yeah, we can easily see the architecture. One nice thing about tracing in general is that you can say, well, you could have drawn this architecture and posted it on your like office wall, right? But I don't know, 2 weeks later, someone comes in, they don't know that, they may see it on the wall, but then someone else goes and says, okay, I'm going to add another service. And what happens to your poster on the wall? You spent like $200 printing it at Kinko's. Does Kinko still exist? But so like, the documentation for architecture is always out of date, right? Whereas microservices, like you do releases like 100 times a day in a large organization. So everything is changing. And even if you're not necessarily creating a new service every day, you're potentially creating new connections between services because you started to call on some other endpoint in another service, an extra dependency. Extra dependency means back to that pyramid idea, more stuff that can go wrong in your application, in your service, right? And so tracing keeps that up to date. So because it just observes what actually happens in production, it knows all the dependencies, and you can always go back and say, yes, that's the actual picture of my architecture, all right? So that's a very useful thing. But now let's look at the actual trace, right? So notice how Jaeger automatically recognized all the services and show them here that were involved in this application. It also it traces itself, so you have Jaeger query as a service as well showing up here, but whatever, we're going to skip that. So front end, I'll pick front end because that's the top service where the requests come in. And I search for traces and I get this one trace /dispatch. And we can see the latency is 730 milliseconds, which was, what did they say? 37, right? The difference is the networking. So this is measured from the front end. This is measured from the back end only. So it's shorter a bit. And then if we go to that trace, we see that picture, which I'll also show in the slide later just to, or maybe I'll skip the slide since I'm doing the demo anyway. So very classic view of distributed tracing. It's a Gantt chart. So what do we get here? So on the left, we see the hierarchy of calls that the services that were involved in executing the single request and in which order, right? There's like a parent-child relationship between them, a hierarchy. Then horizontally, there's a timeline, and every service executed a certain operation. It may have been waiting for something else, but that operation is called a span, and it's represented with a block, which is proportional to the duration of that operation. And then at the top, we see here this thing that I'll just hide, this one, right? Shows up. It's a mini-map. It's the same view of the Gantt chart, but collapsed, so that if your Gantt chart itself, I don't know, 100 lines of 100 pages long, potentially, in a large trace, then Minimap will still show everything. You can kind of easily navigate, if you want to, through that. And finally, the Gantt chart itself, like what's useful about it, right? So certain things are may jump out to you. So you can see that there are a few operations that are marked with an exclamation point. So those tell us that there's an error in that operation, right? Jaeger UI is actually smart enough that if I collapse this whole operation, so everything that driver was doing, then you notice that it also got this exclamation point. It's kind of bubbled up because there were errors. So if we don't see them, we want to see that on the parent span. And I can, like, if I collapse everything, it will also bubble up to the top thing, right? Maybe if it's too small, I can actually make it bigger. It should still work. Right, so like right now there's no exclamation because we do see that. So what else can a trace tell us? Well, so we can trace down the problems like specific like execution errors already. Another thing we can immediately tell is like if we investigate in latency, maybe our SLA for latency is broken. Then we want to see bottlenecks, hotspots in the request. And clearly there is this thing called MySQL select, which takes like, I don't know, 40% of the time. So if we were to optimize that, we would probably look at that as the first thing, because it's the largest thing on a critical path clearly here. And one of the sort of a hidden power of traces, so when we look at this like a high-level view of what execution of the request looked like, we're getting a macro picture, right? There's not a lot of information here, just like which service called which service and how long it took. But what happens if I click on this one? And suddenly I get this whole other set of details about this single operation. right? I can see, let's say I can expand the tags. I can see a whole SQL query that was executed within that database call. I also see like a process information, like host name, which host this was running, and things like that, right? You can enrich this with your instrumentation in any way you want, like pod, region, zone, whatever. So, like, not only you know logically which service executed this request, but like which specific service or instance of that service. And that in that way, tracing provides a micro view as well of your like individual operations and a macro view of the whole transaction across the architecture. There are other things that you can see this tick marks on the span. Let me see what they are. So there are so-called logs. So logs are interesting. Actually, we see a lot of them on the top level request. So I can look at that. So we see 18 logs here. And if we look at this, it actually looks like almost like a regular logging, right? And it is a regular logging. If you look at the source code of the application, what it does is actually just called logger.something, but it does it in a way that that information is not only written to the standard out, and by the way, if I switch to this one, these are all the same logs in the standard out, you can see. But it also writes them to the span in a trace. And which one is better? Well, this was kind of like readable as well in a log, but this is a single request I executed. What if I was doing like 100 of them per second, right? How would you look at them in a typical log stream? You would need to correlate them somehow. You need to like select a subset of the ones that actually belong to my thread or execution thread. In Go, there's no such thing as execution thread. There's no ID that I can put on a thing, right? But in a trace, you are guaranteed to get the logs which only correspond to this single request, to this specific span, right? And more than that, there, like I mentioned, there's another span here, and so it also has the logs, right? So you get the logs which are very contextualized to the place in your execution workflow where they actually happened, not just randomly in some like pile of text that you get with logs. So it's all collapsed into one tool where you can easily investigate the problems. Now going back to latency, so okay, let's say we solved this thing. We, I don't know, optimized our SQL query or did something, maybe put an index on a table and it becomes much faster. Another potential latency we see here is this operation. So it's taking, 200 milliseconds by itself. But what really happens is that it makes this a whole bunch of calls to Redis. And all those calls, as we can see, they're happening one after another, right? So it's a very clear pattern from the visual representation of the trace. It's like a staircase pattern, right? And you can immediately tell that that's probably an issue, that it most likely you can optimize this into some parallel thing. Or maybe you're, like, in this case, those actual requests go into the Redis, so you can do them all in parallel. But what I've seen in practice, people don't often realize is that when you use an ORM, like object relational mapping libraries, and you write in a loop, it looks like it's very tight, but turns out that behind the scenes, or I'm actually making a database call for every iteration of your loop, right? And so instead of doing that, you just want a single request and load things in bulk. And suddenly people get this, like, I improved my performance using tracing by like 10x, right? Like we published blog posts with Grafana and Cortex, like they did exactly that. It's not like some brilliant like feat of engineering. They found just very stupid thing that like very easy to fix, but very hard to find. But that's the challenge, right? And that's what tracing helps. It helps you to find these places in architecture where there are certain things that you potentially can fix very easily. And so, okay, I'll skip that one. I mean, there's like, since I'm here, let me just finish this one. So this is interesting. Like, if I collapse this thing, we can see that there are a whole bunch of requests going on, right? And unlike the previous staircase patterns, these are not exactly, because there are 3 requests running in parallel, right? So good news, bad news situation, kind of like 3 in parallel, but why 3? In fact, if I run the same request many times concurrently from the front end, we will start these 3 operations, we will see them drifting apart. Because what happens in the application is actually there's a thread pool limited by size 3, right? And so when you have a single request, you get the 3 parallelism, but then because this one is doing 10 requests, so obviously that's not enough, so you still have a staircase pattern, but just of groups of requests. When you have a lot of concurrent requests going through this application, then they all kind of start competing for that same thread pool. And so again, fairly straightforward to see that on the trace. It may not be straightforward to fix an application. Like in this case, in the demo application, if you go through the blog post, there's like a command line parameter you can pass to the application to take care of this. And you can see like how the whole trace shape changes. Like you can, for example, reduce the simulated time of the MySQL query and then like make it much smaller. You can't make this parallelized because that would require actually rewriting the code. But this one you can change the parallelism of the thread pool easily. So I think that's, let me switch to the slides and see if I missed anything. So we talked about the service graph, right? We talked about the timeline, the hierarchy, the timeline, the blocking operation, the staircase, so like a nesting of the parent and child spans that kind of represent waiting one on another. And we talked about span details drilling into that thing, database query, some logs. So that's a new feature since last year in Jaeger. So when you're doing performance optimization specifically, think about it like, have you ever optimized something like, or debugged the memory leak? How do you do that? You typically take a snapshot before, take a snapshot after, and you compare them, right? And so when you look at the single trace as we did before, as we see, it's a lot rich information like in there. But if you're actually trying to troubleshoot the regression and performance, it may not always be helpful. For example, let's say you got an alert that your SLA is broken. It's like suddenly from, I don't know, 700 milliseconds it went to 900. You go and you look at the trace and say, oh, MySQL 300 milliseconds or 500, whatever. But what if it's always 500, right? You can't tell from that single trace. So you what you want to do is like at the difference, what the normal trace looks like and this one looks like. And that's what we've built in Jaeger is that you can select two traces. You can do it like, I think we can do it in, let me see, quickly in the UI. So go back to this one. Let me do a few more requests. So if I search for them, so we're getting a lot of this, a bit smaller, a lot of this. So you can just select some of them, right, and compare. And you get this thing. Like this graph is not as interesting as the slide. That's why I'll switch to slide. But yeah, you can do that in Jaeger UI today. If you know which traces to pick, but that's a challenge. So this one is probably from Uber, like from production. It's a lot more complex. There's obviously there's like 100 RPC calls in this one. But it's a div. It's like a code div, right? You have red and green, meaning like red is missing something from the right side. Green means it's added to the right side. And what it's helpful to do is like it's helpful in troubleshooting problems. Basically, you can see that if you're trying to understand how the behavior of the execution of these two requests is different, you can immediately tell, well, this bottom segment in red was like the whole section was missing from the second trace, right? And so something went wrong above that, probably that caused this not to execute. But you can just immediately see that. And if you didn't have that tool or that kind of tool, then potentially it's okay, so like it's a trace with 100 requests in it. Try to figure out where is actually something went wrong, right? There are some more details here. Like the light colors mean that spans are present in both traces, but in different quantities, right? So you may have like more spans in one versus less in one. So like the graph, one of the other features of this graph is that it's not, it doesn't represent every single span from the trace, because that would actually make that graph almost as complex as a Gantt chart itself. And for large traces, Gantt chart becomes a bit unwieldy to use. This one collapses a whole bunch of things. So like if you're making like this Redis call in the previous example like 10 times, this would be probably just 2 nodes. Because, well, what's the difference repeating them? Structurally, they're the same. And so, but if the number is different, you will see the difference in the light colors. So this was like it was indeed the production like from Uber Eats, and there was some issue with what it says. You have an outstanding balance due to credit card problem. So we couldn't charge the credit card, we couldn't complete the transaction, and that's why this whole section of the overall request failed. It never got executed basically in the second trace because we failed on a transaction earlier in a thing. Another thing which is kind of the same visualization but different color coding, which could be also useful, is again, when that example what I gave with if you investigate in a latency regression and your MySQL span takes like 40% of the time, always, it's not useful to look at it. But in a diff, we can suppress it if we use like a heat map color coding of like which things contribute the most to the differences in duration, right? And so when you do that, you can immediately see here what path the differences are, right? Where's the biggest contribution to the latency between the two spans, between the two traces coming from? So that's, again, it's same kind of principle, but just different color coding, and you can probably come up with other things to do that. And there's like because fundamentally behind these traces, they're full Jaeger traces, so you could also obviously do this like pop-ups on individual nodes. And you can also deep link from every node to the trace within the specific place with that trace, which is helpful. Like, again, if you're dealing with a trace of, I don't know, 2,000 spans, the Gantt chart is very unwieldy. It's long. It's like wide. All the spans are probably tiny because you have like a long timeline, but all operations are small within that. But if you deep link to a span, you know with the exact place within the architecture, you can like zoom in into that and drill down, and you can get a lot more rich details. But after you already like use this view to isolate where you want to look for. Okay, so just in summary of the demo. So we see that tracing can be used for monitoring distributed transactions in architecture, monitoring and troubleshooting, but like in general. You can do root cause analysis, what we've done with like latency, with the errors, etc., looking in details. We can obviously use it to optimize for latency and for performance, which is kind of just another side of the coin of overall root cause analysis, or like, because ultimately performance of an application doesn't mean performance in speed or anything. Performance could mean correctness, it could mean availability, and it could mean real raw performance, right? And finally, we can like automatically produce service dependency diagrams with tracing. And one thing that I haven't talked about it, I will skip that because it's kind of tendential to the talk, but Jaeger libraries provide distributed context propagation function, which is not only carrying trace ID, but you can carry other information. So you can like tag your request with a specific product line. Let's say, oh, this is like a Gmail versus, I don't know, Google Docs, right? So two different business lines in Google, they probably at some point all come to the big table. And so how do you, if you're the big table owner, as a service, like how do you basically know which customers are using you? What's their capacity planning? How do you basically, well, how do you tell anything about what the usage patterns are of your service, right? Because, well, the product, Google, like Gmail or Docs, it's like way up front, too high from the like shared platform here. And so by using context propagation, you can tag the request and basically get that information all the way down and emit metrics basically tagged with this information as well. And I think at this point, I'll pass to Pavol to talk about more on the Jaeger project. The clicker.
So Jaeger is not only a distributed tracing tool, it's a whole platform. We have different bits of pieces. So starting, we have instrumentation libraries which implement open tracing API in different languages. Then we have the whole trace collection backend which collects these traces from the clients. And then there is also visualization part which visualize the trace in the UI. The last part is kind of optional data mining platform which gets the traces from the storage, does some analysis aggregation, and stores them back to the storage for later presentation. So Jaeger, it was basically the architecture inspired by Google's Dapper paper and OpenZipkin. It was created at Uber in 2015 and open source in 2017. When it's also joined the CNCF as incubating project. I think last month where Jaeger graduated as a top-level CNCF project. I would like to thank you to all of the contributors who made this possible. So about the architecture, this is just high-level view as the backend is more complicated, but in this case, we see the services. And the important part here is that service A is instrumented with Open Tracing API. It's using Jaeger client, which implements the API. And service B is instrumented with OpenZipkin or OpenCensus or OpenTelemetry SDKs. And both these services, they report data to the same backend, and backend can connect these two spans together and visualize them as a single trace. So in Jaeger, you can collect data from different libraries. The other interesting part on this slide is that Service A and Service B, they can use, even though they are instrumented with different SDKs, they can still propagate the trace because the context propagation in Jaeger is pluggable. When we zoom into the Jaeger, this is basically the architecture. On the right side, we see the host or container, your application instrumented with a Jaeger client. Jaeger client sends data to Jaeger agent, which runs on the host. So in Kubernetes, it can be sidecar container or daemon set. Then the agent sends data to the collector, which then stores the data to the storage, and the query gets it from the storage and visualizes them. Then there is a Spark job, which does the aggregation on the data. This is used at the moment for dependency links. What you saw, the first slide from the demo. So this used to be the traditional architecture, the simplest thing what you can deploy. We kind of improved that by using Kafka. So Jaeger collector is able to write the traces to Kafka. And then there is a new component called the ingester, which gets the traces from Kafka and stores them into the storage. This provides more flexibility and elasticity. So instead of only getting the traces from the Kafka and storing them to the storage, we can also have like a streaming pipeline to do analytics in a real-time fashion. So on the technology stack, the Jaeger itself is written in Golang. There is a pluggable backend layer. As a part of the main project, we bundle implementation for Cassandra, Elasticsearch, Badger, which is in-memory storage, something like Prometheus, and in-memory, which is used for demos. The front end, it's React-based, and then the instrumentation libraries for many languages, starting Go, Java, Python, Node.js, C++, C#. I think the PHP and Ruby are community-based. Again, integration with Kafka and Apache Flink, but also Apache Spark. The Flink is kind of new, the new way the streaming works, and the Spark is used for the old job, which gets the data on a daily basis. For the community, at the moment, I think we have around 9,000 stars on the main repository. A lot of contributors. We have 15 maintainers across all the repositories. We are happy to accept more. And we did 15 releases since the start, basically. So what is new in Jaeger since the last KubeCon? We implemented the operator for Kubernetes. This operator is able to not only deploy Jaeger, manage it, but also create CRs which will be picked up by the storage operators and deploy the storage. So if you are using OpenShift, you can just create one CR, and the OpenShift, the operator running on OpenShift will get that CR, also create the Elasticsearch for it. So it's very simple to create, like production-ready Jaeger deployment. Then there is a Badger storage, which is local storage, something like Prometheus, just single node. This is by default used in Istio. And the storage layer is pluggable. It's based on gRPC plugin. At the moment, there are two implementations, one for Couchbase and other for InfluxDB. Yuri talked about the trace comparison. That's also new. And we made some improvements on the security part. So there is TLS for the gRPC communication between agent and the collector, and also for the Kafka and Elasticsearch.
Probably want to stop soon because we're out of time.
Oh, yeah. So documentation, I don't have time to go through that, but we have quite nice website, and all the docs are there. You don't have to go to our GitHub repositories to find out about the things. Again, some of the integrations with Jaeger. And I would like to also mention the Zipkin compatibility. Jaeger can receive the data from Zipkin clients and also can talk to Zipkin clients. So if your service is instrumented with Zipkin, the other service can be instrumented with Jaeger, and they can basically talk to each other.
I'll probably skip roadmap for the deep dive tomorrow because we're out of time.
Yeah. Okay, so deep dive is tomorrow, 2:25. You're welcome to join. Thank you very much.